Hi, this is Richard Pickings from Bridgeside Software. Welcome to part one of our two-part tutorial on creating new girder sections in PGSuper. In this tutorial, I'll show you how to create a new girder section and set up geometry and prestressing input options. I'll also provide some insight into PGSuper's automated Flexure Design feature. In part two, we'll discuss shear design and stirrup input options. And along the way, I'll give some tips about how to input girder data and show you some features in PGSuper Professional that can help make the design process easier. In this tutorial, we'll define a standard 66-inch deep CalTrans Wide Flange section. CalTrans Wide Flange sections are based on the Nebraska NU girder shape developed by Dr. Mayer Tadros for the Nebraska DOT. And the CalTrans Design Aid document shown gives dimensions and section properties for this shape. The section contains both straight and harp strands, all spaced at 2 inches. And notice the straight strand bundle is located 3.5 inches from the girder center line. At this time, PGSuper has 15 parametric girder types to choose from. 12 of the primary types are shown here. And depending on their type, sections can be spaced adjacently or wide spacing. Some sections allow the input of end blocks and shear key loads, and there's even an I-beam section that can have a tapering depth. But a quick look at our sections here reveals that our section will be based on the Nebraska NU type. Once a girder section is defined, it can be referenced in a PGSuper bridge model and used to design prestressing for a bridge. Of course, PGSuper is a pre-stressed girder design program, so getting the girder data correct is really key to success with a program. If a girder entry is poorly defined, it can result in bad computations and cause PGSuper's design automation algorithm to fail, or at the very least come up with suboptimal designs. So you really need to plan out and use your engineering judgment and not a small amount of testing when you create a girder library entry. Girder sections live in the PGSuper library and describe the geometry, prestressing, shear reinforcement, longitudinal mild steel reinforcement, and the interior diaphragm layout for a girder. Since girder sections live in the library entry, there are two places where you can define and operate on them. You can work either in the master library file using the library editor, or edit a local girder entry directly in a PGSuper project. I find that working directly on a master library file, it can be laborious. Basically, you have to make edits in the library editor, save the library file, then open a PGSuper project to test your entry, and then repeat this process until you finally got the entry right. So personally, I prefer to work on local library entries contained in a project and then move them to a master library file once I have the data just the way I want it. It's just easier to do it this way. First, we'll configure PGSuper to use the CalTrans DOT configuration that's available at PGSuper.com. If you're using PGSuper Professional, you'll already be set up to use the PGSuper.com DOT configuration libraries. If you're using the free version, you'll have to configure the PGSuper to access these, and instructions are provided at the PGSuper.com website. So open PGSuper with no open projects, and then go to File, Configure PGSuper. Then select the PGSuper.com community server and the CalTrans PGSuper library. To open the library, click on Update Library and Templates Now. So now we're ready to create a new CalTrans Bridge project file. And just a side note here, PGSuper.com's CalTrans library already contains the girder we're going to create for this tutorial. But for learning's sake, we're going to start from scratch. If you're new to PGSuper or starting a set of libraries and templates for the program, I recommend starting with the project criteria library that disables the options for haunch design and lifting and hauling design. This forces the girder design algorithm to focus on strength and service design and will help you over better understand the overall behavior of your new girder. And also it allows the design algorithm to run faster. And once you've fine-tuned your new library entry, you can go back and turn the design options on. Okay, I'll open a new PGSuper project based on the CalTrans IG48 template. And it really doesn't matter which template we start with, since we'll be changing the girder type to our new section once we've created it. This particular template is based on an old CalTrans shape that is based on the Ashto standard girder. So let's go to the library editor and see what we have. A quick look at the project criteria shows that we're using the CalTrans LRFD 2008 entry. The project criteria defines agency-wide settings and high-level settings for all PGSuper projects in an agency. Let me go ahead and open this and click on the Design tab. And what we'll see here is that the slab offset or haunch design, lifting, and hauling are all turned off for the automated designer. So this is good. I'll go ahead and close this. And let's go to the girder library. As you can see, there's already a bunch of girders in here. And one thing you'll kind of quickly notice, there's a WF66 that's really the girder that we're going to input. But let's start from scratch by right-clicking in a blank area in the library window and click Add New Item. I'm going to call this my WF66 and hit Enter to open it for editing. You'll notice real quickly here that this isn't the shape we want. We have a box shape, and what we want to use is the Nebraska NU. So I'll go ahead here and pick the girder type, Nebraska NU girder, and that brings up a picture of the girder we want. First thing to do is we need to input the geometric shape parameters. These are all shown in the schematic here, and you enter them in the grid. And the goal here is to match the geometry and properties of the CalTrans shape as closely as possible. I'm going to skip ahead here so we don't get bored with the gory details. Okay, I have my geometric parameters input. Let's take a look at the section and see how well I did. I'll click on View Section at Ends to take a look at the end of the girder. This is prismatic, so it doesn't matter which end we look at. Whoops. Looks like I got my top flange wrong. Let's take a look over here. Oh, I see. Dimension D1, it should have been 3 inches instead of 1. Let me go ahead and change that. View the section again at girder ends. And that looks better. Notice that the section view also shows section properties for the girder. This is very useful for getting your section dialed in correctly. As I mentioned earlier, our goal is to match the CalTrans shape. This not only means the shape geometry, but also the section properties, such as area, moment of inertia, and CG locations. For some cases, that you'll find that the section properties don't match exactly, even if you get the geometry perfect. PGSuper computes the properties exactly for the input shape. However, oftentimes the engineer who first developed the shape made approximations when computing the properties. For instance, items like fillets and chamfers may have been ignored during the initial shape development. This can be a problem from some sections, and you may find that the properties don't match as well as you want. So you may end up having to tweak the shape a bit to get the section properties to match. I'm typically satisfied if I can get all structural properties to match within 1%. Here's a quick tip. The input grids in PGSuper in general are like Excel grids. You can select entries in the grid and use the Control-C and Control-V commands, standard Windows commands, to copy and paste data. This can come in real handy. Okay, now we've finished the basic shape geometry properties, next thing we do is to go on and look at prestressing. And since we have both harped and straight sections, let's take a look at the harping point locations. These are where the hold downs are. Okay, CalTrans typically, they will have the harping point located from the end of the girder at 40%. So let's go ahead and enter 0.4 for the harping point location. Next is the fun part, input of the permanent strands. But first, let's take a little time to talk about how harp strands are defined and used in PGSuper. Here's a photograph of a typical casting bed in Washington State. The workers are just setting the strand locations before the forms are to be placed. I want you to notice two things about this photo. First, take a look at the strand template plate at the ends of the girder. The template plate can be adjusted vertically by moving the jacking frame up and down. This means that strand locations at the ends can be adjusted continuously up and down, not just at 2-inch increments, but any increment. However, the relative distance between the strands is typically the same, 2 inches. Second, look at how the strands bundle together as they approach the hold down location. At WashDOT, strands are gathered or bundled together into a single location at the hold downs. And like the strands at the ends, this bundle can be moved up and down continuously. PGSuper uses this continuous vertical adjustment concept to locate harp strands in a girder. You must first define a strand template or bundle that defines the locations of the harp strands relative to each other, and then you can adjust the template up and down to create harping. Armed with that information, let's go back to PGSuper and input some strands. Web strands, in our case, are harped. You can also create web strands that are always straight along the length of the girder. This comes in handy if you want to allow a bundle of straight strands that can be adjusted vertically. Use different harp locations at girder ends. This refers to the relative locations between harp strands at the ends and the hold down point. Turn this on if you have bundled strands like WashDOT, but leave it off if your strands remain parallel along the entire length of the girder. Most agencies use parallel harp strands. CalTrans harp strands are parallel, so we turn this off. Coerce odd number of harp strands. Strand locations in PGSuper are typically input in pairs, as we'll talk about in a moment. However, you might want to fine-tune the number of harp strands, being able to add them one at a time. This option will force the location of the topmost pair of strands to be at the x equals 0 or center line of girder, and hence allow an odd number of strands. Now let's start entering strand coordinates. On the grid here, we'll click Append. The first strand or pair of strands that we're going to add are straight at 3.5 inches from the girder center length and 2.5 inches from the bottom of the girder. I'll click OK, and this created 2 strands. I'll click OK again to append more strands. This time I'll make a harp strand pair. So they're harped. X is at 1 inch from the girder center line and 2.5 inches from the bottom. Click OK. Now let's take a look at what we've created. Here are our strands. Okay, our 4 thus far. Let me go ahead and move this harp strand to x equals 0 and take a look again. As you can see, when x equals 0, it puts a single strand at the center line of the girder. A non-zero x value creates a pair of strands. A common question for first-time PGSuper users is, Do I have to enter these strand locations for every girder and every bridge I create in PGSuper? That'd be crazy. No. We define a girder entry to have all the possible locations for a given girder type, and then in the bridge model, we fill those strand locations for a specific girder in a bridge. You can think of the girder library entry as a standard plan, much like that CalTrans bridge design aid we saw earlier in the tutorial. Okay, 4 strands down. We have 68 possible locations. As you can see, this is going to take a while. Maybe there's a better way. This looks promising. Generate strand positions. Let's go ahead and delete the strands we have by clicking delete. Select the strand, click delete, and let's see about generating strands automatically. The Generate Strands dialog allows us to generate a whole bunch of strands at once in a uniform grid. So let's try this with our straight strands. Okay, we got straight strands. We're going to have a start point and enter the vertical and horizontal spacing. We're going to fill them sequentially. Let's start at 3.5 inches from the center line of girder for X and 2.5 inches from the bottom. Our spacing between strands is 2 inches. Horizontally, we have 9 strands per row, and we want to generate 4 rows. This will generate more strands than we want, but let's see what happens. Again, let's view it ends. And as you can see, this generated all of the strands we need, all the straight strands we need, and a few more. Fortunately, it's pretty easy to delete strands. Let's take a look here. We need to delete strands 61 through 72. And then also strands 49 through 54. Let's go up, strand 61, and click delete. That will get rid of those. And now go up to strand 49. And let's get rid of those 6. And let's take a look. Hey, that's a lot better. That looks exactly like the CalTrans plan. Okay, now that we're done with straight strands, let's go on to the harp strands. So again, strand type, harped. Okay, X is 1 as we want. Y, 2.5 inches from the bottom. Spacing again is 2 inches. We want to generate 1 column of strand on each side of the girder and 7 horizontal rows. Okay, let's take a look. Much better. And we have 68 strands. That's exactly what we wanted. This looks pretty good thus far, but there's one problem. We need to look at the order in which strands are filled. The order in which strands are filled is very important for multiple reasons. In PGSuper's versions prior to 2.7, strands could only be input by specifying the total number of strands in a girder. Taken together, the fill order and the number of strands is enough to specify exactly which strands are filled in this section. For instance, if you say fill 40 strands, the program will fill the first 20 locations as we define in the grid right here, and the grid actually counts the locations for us, so it will have filled these first 40. And if we look at the schematic, we can see that our first 40 strands are all straight strands. Might not be what we want, because typically we fill from the bottom row to get maximum efficiency from our prestressing strands. Agencies like TxDOT and WashDOT actually specify fill order for their strands on their standard plans, and PGSuper respects this. For instance, TxDOT fills strands from the bottom up and inside out. If the strand order is not specifically specified by your agency, you'll need to use your engineering judgment to come up with your own fill strategy. Bottom up is always a good strategy. But we can easily change our strand order in PGSuper to match TxDOT's strategy by using the move function. So let's move our harp strands so that they interlace with the rest of the global strand fill order. So I'll grab our harp strand here, the bottom one at 2.5 inches, and click on Move Up until it's the first strand in the order. We can also do this with the other strands. Okay, we have our fill order complete. Here's our girder thus far. Another very important consideration when creating your strand fill is PGSuper's automated design algorithm. The design algorithm has two different options you can choose when filling straight harped prestressing patterns. Let's open the project criteria to see what these options are and what they mean. Our current project criteria is CalTrans LRFD 2008. We can tell it's currently selected for this project by the red check mark next to the library name. The lock symbol tells us that it's contained in the master library file and is read-only. I'll open it by double-clicking and go to the Design tab. There's two options here for the strand fill order used for automated harp pattern design. The first is to strictly use the global strand fill order as we just defined it in the girder library. This means that the design algorithm doesn't have any flexibility in the way that it fills harp and straight strands. The number of straight and number of harp strands is fully dependent on the fill order. TxDOT uses this option. The second option is to try to minimize the number of harp strands. For this case, it fills straight and harp strands independently, but still uses their relative order in the list to fill each strand type. The algorithm will usually move harp strands at the ends to their highest allowable location and try to use as few harp strands as possible. WashDOT uses this option. So which option is best? It really depends on the policies of the agency that you're designing for and on your engineering judgment. I find that option 1, strictly using the global strand fill order, gives more control over the design process and for me generally ends up with better designs. Your mileage may vary here. Let's go back to our girder entry and finish up the strand input. The last item to talk about on the Permanent Strands tab is the allowable range for vertical adjustment of harp strands. Remember our photo of the strand template in the Washington casting yard? This input defines the vertical range in which the strand template can be adjusted. Most agencies do not allow the template to be adjusted at the hold downs. For CalTrans, the bottommost strand layer at the hold down is 2.5 inches from the bottom of the girder. This is where we input the strands, so no adjustment is needed or allowed. So we disable the adjustment at the harping points. However, we do need adjustments for the harp strand group at the girder ends. This is what allows us to move the strand group upward to cause draping or harping of the strands. For this girder, we will set the bottom limit at 2.5 inches from the girder bottom and the upper strand limit at 2.5 inches from the top of the girder. The design increment tells the automated design algorithm to raise or lower the strands in 2-inch increments. This will create harp strand adjustments with nice round numbers. Before we save our new girder entry and use it in the bridge, I want to talk briefly about one more important item for flexural design, and that's debonding of strands. PGSuper allows you to debond straight strands, and it allows you to mix harped and debondable straight strands in a girder. However, the automated design algorithm cannot do both. If you have any harp strands in a girder, the algorithm will do a harp design with no debondable strands. If you have a girder with all straight strands and some straight strands that are debondable, the design algorithm will attempt a debond design. You can set debonding quantity and length limits for the girder on this tab. These limits are specified in section 5.11.4 in the AASHTO LRFD, but are often overridden by DOTs and agencies. Refer to the Bridge Design Manual for your agency for guidelines on this issue. Well, for now we're done with the input for the geometry and the prestressing for this girder. This provides enough data to allow us to look at the flexural analysis and design input. Let's save our girder entry data by clicking OK, and let's put our new girder to use in this bridge. I'll go to Edit, Bridge. This brings up the General tab. We can go ahead and select our girder type for the entire bridge. This will be our new MyWF66. And this brings up a dialog. What's this telling us is that whenever you change the girder type, PGSuper will reset the strand, stirrup, and longitudinal rebar data back to defaults. This means that the number of strands will be set to 0 in the girder for the new girder type. So we'll go ahead and say OK and OK. Let's take a look at the bridge view. It looks a lot like a Nebraska NU girder. Let me right click and go to View Girder. And again, this looks like our new girder shape. Now let's go ahead and add some strands to the girder. I'll double click on the girder view and go to the Girder Editor tab, the Editor dialog, and then to the Strands tab. Here's where we define the number of strands that are filled in an individual girder. And for our first case, let's go ahead and use our global strand fill order and use the total number of permanent strands. I'll go ahead and define 30 strands in this girder. Okay, the next thing we need to do is adjust the vertical location of the harp strands. As you can see, the datum for doing this right now is the distance between the CG and the harp group and the girder top. Let's go ahead and change this to the distance from the bottommost strand and the girder bottom and put our strands at 2.5 inches. I'll go ahead and click OK. And what this did was make our harp strands straight. Okay, that's probably what we don't want to do, so let's go back and offset the strands upward. This text right below the input tells us the valid range for our strands. So let's go ahead and move these strands all the way as high as they can go to 61.5 inches from the girder bottom. Click OK. Okay, now we have some significant harping. And if we go to the end and make our view a little bigger, you can see that the harp strands have been moved pretty much as far to the top as they can go. Next, let's run the flexural design algorithm. From the main menu, we can click Project Design Girder. Notice we're working on girder B in the system. This is the girder design dialog, and for this tutorial I only want to design for flexure. In part 2, we'll look at designing for shear. I'll run the design algorithm, and it comes up with a proposed number of strands to add to the girder. 22 straight and 4 harped. The distance from the bottom of the girder to the harp strand group is 38 inches, so it puts it a little more than halfway up the girder, and we have a good low concrete strength. I'll go ahead and accept the design. Let's do a quick review of our design using the BridgeSite Girder Design Dashboard. The design dashboard is one of many enhanced features in our PGSuper Professional product. The dashboard is a great way to check the overall health of a girder and also enables you to input changes to prestressing and concrete values without opening any other dialogues in PGSuper. The green backgrounds in each graph show that each limit state in question passes the spec check, while red areas indicate a failure. We can see very quickly that the primary flexural stress and strength cases have passed the specification check. The red in the ultimate shear graph tells us there's work to be done before a shear spec check will pass. I'll talk about shear design in part 2 of this tutorial. As we saw before in the girder view, our current design has a relatively low level of prestressing and a minimal required concrete strength. Maybe we can fine-tune this design. As we might know, most precast manufacturers prefer not to use harp strands if they don't have to. Harp strand designs require more labor and cause safety concerns in the plant environment as compared to an all-straight strand design. So let's see if we can straighten out those harp strands using the girder design dashboard. First, I'll straighten out the strands by lowering the harp strand bundle at the ends to 2.5 inches from the girder bottom. This will make the strands straight. Note that now stresses at release are failing. LRFD 5.9.4.1.2 allows concrete tensile strength at release to be increased if there's significant bonded mild steel reinforcement. The amount of rebar is minimal and most plans provide it, so let's enable this option. This still doesn't cause us to pass a spec check. But if we look up in the stresses at release graph, the design dashboard indicates that we need 4.4 KSI concrete strength to pass our specification check. So let's go ahead and increase F'(CI) to 5 KSI. Excellent. Now we've passed all flexural spec checks with an all straight strand design. Our precaster will be happy about that. Notice that the control center still indicates that the spec check is failing. This is our shear issue. Let's click on View Girder to make sure that we have an all straight strand design. A quick look at this tells us that we do. As you can see, the girder design dashboard enabled us to refine our design all in one view. No switching back and forth between reports and dialogues. One last item to talk about. Okay, we've created a library entry, but it's local to our project and can only be used in this project. How can we share it for use in other projects? The answer here is, of course, we need to put it into a master library. And I'll show how this is done using the Import Select Library Entries feature in PGSuper Professional. First, let's go ahead and save and close our project. PGSuper allows you to open multiple different file types. One of the file types are master libraries. Another one that we've been working on is our project files. We're going to go ahead and open the CalTrans master library file. Master library files end with an LBR extension. I'll go ahead and take a look at the girders in this file, and we'll see that my WF66 isn't in the file as would be expected. So I'll go ahead and import select library entries and pick the file that we just saved. And this will bring up a little tree that we can use to select which entries we'd like to import into our library. Our case, we just want my WS66. Click OK, and here it is, ready to be saved in our master library file and then shared with other projects. This concludes part 1 of our tutorial on how to create girder library entries in PGSuper. I hope that I've given you some insight in how to create your own girders and how to use libraries in PGSuper. In part 2, we'll discuss transverse reinforcement. In the meantime, thank you for using PGSuper and supporting the PGSuper project. Please make sure to check out PGSuper Professional. It's a power-packed version of PGSuper that gives you tools that can take your precast designs farther. Until next time, this is Richard Pickings from Bridgeside Software, wishing you successful bridge design endeavors.